Get the recording started just so I don't forget. Give it a couple more minutes and then we will get going. As long as we got show and tell here. Tom, I know this is kind of in your ballpark. This was a project I just finished. I got this from the SpeedX key. I got it from Toby's estate. It was a little rough. It was missing the contact post. Somebody had replaced it with a brass screw and a couple pieces of perf board as an insulator, and the factory spring was gone. It was just some random spring that was stuck in there, and it needed a cleaning, so I took it all apart. The base, fortunately, was in good condition. There was no flaking on the paint and no corrosion. So I gave the base a good scrubbing, and I cleaned all the metal, and then I took some metal polish and a buffing wheel on my Dremel, and I cleaned up the main lever and the other stuff. And I found out that the last owner of SpeedX passed away at the beginning of last year, and nobody was going to carry it on. It's kind of sad because SpeedX has been around since the 1920s through various owners, but so I got a hold of the widow. There you go.
That's my SpeedX. It's a little bit newer than yours, but
yeah, mine based on this is one from the William Nye era.
Yeah, because it looks like it's got like the spark gap kind of arm, like this old Signal Electric one.
Yeah,
got that spark gap arm.
Yeah. So I estimated mine was around 1976 or so. So this dates back to right around when I got licensed.
Okay, yeah. This one dates to, I think, the 30s. Nice. And the key that I use on my station over there, might be able to see it if I get out of my way. I don't know, but is it's an old Bunnell from the mid 20s.
Okay.
So that's the one I use regularly.
I've got a Vibraplex from 1926.
Ooh, nice.
That was either Western Union or Railroad, and it's in pretty decent condition. I can't use it because I was trained on an electronic paddle, and I've been doing that for 40 some years. My brain can't make the dashes happen. Yeah.
No, I've been using a straight key so long that I gotta really concentrate even if I use a paddle.
Yeah. There you go. Nice, Tom.
There you go.
I reached out to, emailed SpeedX with the address on their website, and the guy's widow emailed me back, and she said, we're just selling off the remaining parts we've got because nobody took the company over. So
yeah, I wonder if what's like the same company that took over Vibraplex and L&R Precision and things like that. I wonder if they'd be interested in picking up the name.
It would be nice because it's a nice key.
Yeah.
But I don't know if anybody's ever talked to them about it. I might see if they are interested and put them in touch with her. But
the last key I bought from them was this little guy.
Oh, that's cute.
So I that goes in my pack when I go traveling and stuff like that. It's a little Camelback, but you can see it's about the length of 2/4.
Yeah,
that's got an amazing feel to it for the size of it.
Cool. She had the contact post.
Yeah.
She said, I sold springs out a long time ago. She says if I had 4 times the amount of springs, I could have sold them.
Yeah. I like the navy knob on that too. I don't have any of the keys with the navy knob.
And no, fortunately, this one was original. I mean, it came with it, and it looked really. I was afraid it looked really grungy.
Yeah.
But then, when I was washing this, I scrubbed it with a little Dawn and a soft toothbrush, and it came clean.
Yeah.
So it's like, all right. So it's got the knob, and then the base plate. She had one left.
Oh wow.
So she sold me because it's got the same crinkle paint that the base part does.
Nice.
So by the time I got it all cleaned up, it's pretty nice. So I have something I can use for straight key night.
Yeah.
I'm forcing myself back into Morse code.
Yeah. Every night's straight key night for me.
Because it's been a long, well, yeah, but it's been a long time since I've really used it.
Yeah.
So it's like that's got a lot of rust to knock off, which is not quite as easy when you get to a certain age.
No, I know. It's funny because I don't want to bump up against time here, but
no, go ahead.
I have a buddy of mine in Austin, Texas that I kind of helped to get into ham radio when he and I worked at the same company, or I should say when he worked at the company that I do. Got him into ham radio a little bit, and actually sent him a whisper beacon transmitter that I've been playing with, and I did a couple of videos on, and he kind of got enamored by low power communications. That got him into CW, and then he started shaming me for being an extra that didn't do CW anymore about 5 years ago. So, since then I've been on a quest to kind of build my speed back up again, because I lost, I learned the wrong way 40 years ago, too slow, and my brain goes through that translation process. That was taking a long time to kind of get out of that.
Yeah, so that's nice, Tom.
Yeah,
Tom is also big in CW.
Nice.
And he's got quite a collection of antique keys.
Nice.
So, but my primary paddle is my Brown Brothers that I've had since I was a kid. That was when I got licensed that Christmas.
That looks like that bolts up on the front of a K2 or something.
Yeah. My Elmer had the Brown Brothers paddle because we lived near St. Louis, so that was people knew about it.
Okay.
And so for that Christmas, Mom and Dad got me that, and I've hung on to it all these years. I've never let go of it.
Nice. What
I really would like is they made a straight key with the same mechanism with the flat metal spring hinge.
Okay.
As the paddles, and they're really rare. So I just keep looking. It was if I meant to have one day I'll come across one. So
right.
All right. Let's get started this evening. There's a couple of new names I see here. I believe at least one of you I had spoken with on the phone, maybe. So if you are new to our Zoom meetings, go ahead and unmute yourself and introduce yourself. Go ahead, don't be shy. Or don't. So well, welcome to you all.
Didn't have my microphone plugged in. That SpeedX cleaned up pretty nice.
Yeah, it did. I'm really happy with the way it turned out. So, and then he had a second one that was in much nicer condition that I cleaned up and sold for him, or for the family. So,
yeah, that Bengali I was holding up. That Bengali I was holding up is one that fits the KX3.
Yeah, that's what Alan was saying. It looked like. Yeah.
On now?
When I always look at their booth when I go to Dayton, and they've got some pretty keys, but they are not inexpensive. So,
yeah.
Hi, this is Frank, WB80NF, and I'm in Tallahassee, Florida. I'm a displaced Buckeye. I grew up near Dayton on a farm, so I used to go to the Ham Fest quite regularly.
Okay, well, welcome, Frank. Where did you find out about tonight's meeting?
On 100 watts and a wire on Facebook.
So you saw my link that I put there. Cool.
I sure did, yes.
All right. Anybody else who's new to our group?
Yes, it's Jim, WA8JIM. I believe we spoke.
You're the one. Yeah, I spoke to you and your wife on the phone.
Yeah, she's right here with me saying hello.
Well, welcome. And for those of you, some of you know, but for those of you who don't, I'm Paul, WD9GCO. I'm president of the club. And so welcome, everybody. For those who may end, I mean, if you have to bail out, that's okay. I'm recording this, and it will be up on my YouTube channel probably tomorrow. And so you can watch it, or you can watch it again and learn. And then you can also share it out to friends who didn't get a chance to see it. So, all right. So let us get on. First off, I am going to spotlight you. So I'm going to go ahead and mute everybody else. Our guest this evening is Alan W2AEW, who I saw give a presentation on YouTube, and also had been recommended by, I think, somebody from the Ham Radio Workbench podcast. It was, it's something that fascinates me because I've got a NanoVNA and I know a little bit of how to use it, but there is so much more that you can do with these things, and they're cheap. I mean, it's not quite as accurate as like a $30,000 commercial VNA, but yeah, but for what we do, I think it's awesome. So I am going to go ahead and I am going to, just for fun, real quick, before we get started, I forgot to mention, there was an online trivia competition about a month ago between the guys from the Ham Radio Workbench podcast and the guys from the ICQ podcast over in Europe. And they decided they had so much fun that they were going to hold a second one, which was between the Ham Radio Workbench crew and us in Amateur Radio Newsline. And that will drop. I'll send out a link to the club. So if anybody wants to watch it, that will drop on the 28th, which is, I believe, a Tuesday, on Kyle, who's the guy who moderated the contest. It'll be on his YouTube channel. And I just found out that there's going to be another matchup between us and the ICQ podcast guys. So it's kind of fun. We have a team, and we're doing ham radio trivia. So that's it. Now, back to our regularly scheduled programming. So I'm going to turn it over now. Alan, it's all yours. Take it.
All righty. Very good. Thank you, Paul. Thanks for the invitation to come here and speak with you guys tonight. Yeah, a little bit about me. I'm a W2AEW. I live in New Jersey. That explains the accent. So I work as a field application engineer for Tektronix, and I guess I've been licensed since about 1979 or 1980 or so. And I work kind of in the technical field, so I get to play with stuff, electronics and things like that for work, and then for the hobby here as well. So anyway, so what we're going to chat about tonight, let me share my presentation here, and let me know if all that shows up okay with everybody. Let me bring up the presentation view. You got that okay, Paul?
Yep, it's all good.
All right. So a little bit of an introduction to VNAs in general, because it's not something that most hams, unless you're in the professional world, get to play with. And then we'll dig a little deeper on the NanoVNA specifically. So I am also the technical coordinator for the Northern New Jersey chapter of the ARRL field organization, and a life member. So anyway, with that, let's get rolling. As we go along here, I should say that if you've got any questions along the way, feel free to stop me. If something wasn't clear, we're better off kind of dealing with that before we move on. So certainly feel free to jump in and ask any questions that you might have. If you don't have any questions, keep yourself muted so that the phone ringing and the dog barking doesn't get on the video here. So here's a little bit of our agenda today. So, why do we want to talk about this? Well, the main reason is that we now have these, as Paul mentioned, these ridiculously inexpensive NanoVNAs that now make VNAs accessible to hobbyists like us, like hams. So let's go explore what they can do. So the first thing we'll talk about is what a vector network analyzer is, what a VNA is. Then we'll talk about what it's good for, what you can use it for. The likelihood is that it can be used for many, many more things than you might use it for, right? You might use it for these 3 things, and somebody else might use it for those 2 things. But we'll kind of cover a little bit of a broad swath of the major applications for a VNA. And then we'll take a closer look at the NanoVNA specifically, and a little bit about the menus and how to drive it and what you can do with it. So the first thing here is, what is a VNA? Okay, as we mentioned, a VNA is a vector network analyzer. And if you Google that, you're going to get something like this, an instrument that measures the magnitude and phase of the reflection and transmission properties of the ports of a device versus frequency. Well, what the heck is that, Right. So let's try to clear some of that up and take some of the mystery out of it. So we'll start by kind of breaking it down. First off, a VNA, it's really an instrument that's used to characterize RF devices. Okay, that sounds good for us hams. And it used to only be used by professional engineers due to the cost. Professional units can cost thousands of dollars or more. The two on the top over here, let me get my pointer going here. These two up here are sub $10,000 units, which are inexpensive VNAs in the VNA world. Okay, this 4-port high performance unit here from Keysight costs $238,000 typical price. So these are expensive instruments. Okay, of course the VNA is nowhere near that. And there's lots of different acronyms and terminology. And I'm actually going to cover some of that because if you do any reading of application notes and things like that to learn how to use your VNA, you're going to come across this terminology, and it's helpful to kind of at least know what we're talking about. So first is DUT. What is the DUT? The DUT simply stands for device under test. Us engineers, we love acronyms. So there you go. So the DUT is device under test. In our case, it might be an amplifier, it might be a filter, it might be an antenna. Okay, maybe oftentimes it is an antenna because that's what probably most hams will use the NanoVNA as an antenna analyzer before anything else. Now, any kind of a DUT will affect the signal going through it. Okay, its transmission properties. And the input impedance of that DUT is going to affect the applied signal because you may get some reflection coming off of that. You may have learned from any kind of study of basic electronics that you get maximum power transfer from some kind of a source, whether it's a power supply or an RF transmitter. You get the maximum power transfer when the source impedance matches the load impedance or vice versa. Okay. When we start talking about RF, we have to think about things in complex impedance. So the more general sense is that you get the maximum power transfer when the load and source are complex conjugates of each other. It just means that the resistive portion matches and the reactive portion is of an opposite sign. If you're going to be designing matching networks, like a matching network for an antenna or something like that, and you're going to design it on your own, you're going to need to know the complex impedance looking into a DUT, and that's one of the things that the NanoVNA is good for. Not something you have to use if you want to just measure SWR, but this is something we're going to cover. And when we start talking about signals in the RF domain, we generally want to think of signals as waves. So rather than thinking of volts and amps, we think of things like amplitude and phase, or magnitude and phase. And phase is just, that phase is one of those terms that can confuse a lot of people. And really all phase is in our world here is delay. Okay, if you think a single cycle is 360 degrees of phase. And if you have another wave, if you will, that is shifted a quarter cycle, then it's shifted 90 degrees. And its phase is 90 degrees with respect to this first waveform. So phase is really just another way of expressing delay, but that delay is going to also have, the other piece of it is frequency, because a fixed delay in time will amount to so many degrees of phase at a given frequency. Here, this picture is attempting to kind of illustrate how things can change. So let's say we have a source like a transmitter here and a load, maybe that's an antenna. And you can see the load is getting gradually further and further away from the source. And what I'm picturing here is a signal coming out of the source. That's kind of the bluer colored line going up to a load and then creating a reflection that comes back. And you can see that the phase between the incident wave and the reflected wave, the red one, will change. It will depend on the distance between the source and the load. So it's just another way to kind of think about what phase means and why things like transmission line length can actually alter the complex impedance, because the phase changes depending on the length of that line with respect to the frequency you're using. So let's think about this in terms of measuring a device. Okay, I've got a source that's generating an RF signal going into a device. It's going to send its signal up to the input port of that device. Some of that signal, depending on what that device is, may go through it, right? Might be a filter, might be an amplifier or something like that. So we call that the transmission properties of the DUT. Now, if you don't have a perfect impedance match at that input port, you may get a reflection off of that port, and that energy gets reflected back towards the source. Okay, so we call that the reflection properties of the DUT. So, and of course, the VNA is good at measuring the transmission and reflecting properties of a DUT. Okay, so the DUT's reflection and transmission will alter the magnitude and phase of the source signal. And that's what the VNA looks at. Okay, so let's go see how we use that information to compute various things. So this is a really basic block diagram of what's inside of a VNA, like the NanoVNA, right? There's an RF source right here that sends a signal out through port 1 to our DUT. Okay, you'll notice that we have a pair of these pictures here are directional couplers. And what they're designed to do is pick off a sample of the signal going in this direction, okay, the incident, or in this case, we're going to call it our reference signal. That's what we're sending to our DUT. And then this directional coupler is picking off a piece of the signal that's coming back from the DUT, the reflected signal coming back, and that's getting picked off by this directional coupler. Now, inside the VNA, there are 3 receivers, okay, we'll call it the R, A, and B receivers. Those receivers are measuring the magnitude and phase of the incident wave, the reflected wave off of the input port of the DUT, and the response coming out, or the transmission response coming out of the DUT and coming into port 2. So the B receiver measures the transmission properties, the A receiver measures the reflection properties, and then the R receiver is the reference that we're going to compare those to. All those receiver results are computed, and we display various results like return loss or reflection coefficient or transmission coefficient or VSWR. Those can all be computed from the outputs of these receivers. So again, the transmission properties are based on the B with respect to R. We'll call it B over R, right? It's our response coming out through the device with respect to the signal being injected to the input of the device. So that's why it's B over R. And this could be measuring like gain or loss, again, of an amplifier or a filter. It can also, another way of expressing that is something called S21. We'll talk about S parameters in a moment briefly. Okay, don't get scared. They're not that bad. Okay. This is also known as the transmission coefficient of the device. And then you could also measure things like the insertion phase or group delay through a device. If you're not an engineer, you may not care about those. Don't worry about it. Okay. And then port 1, these are our reflection measurements, right? We've got our incident signal coming into the input port, reflected signals coming back into port 1. These are our reflection measurements, and they're based on the A divided by R, right? The A results divided by R. So that gives me A with respect to R, right? If the results in A equaled R, that means I'm getting a perfect reflection. Everything's coming back like it was a pure open or a short, for example. Now, based on that A versus R, we can compute VSWR, which is probably the thing that most hams will use a NanoVNA for. We could also compute something called the reflection coefficient, okay, or S11. That's also known as, you just change the sign of it, and it's called the return loss. And then, and even can compute the complex input impedance. So all those can be computed from the A and R measurement results. Now, most professional VNAs will have a set of couplers and a source on both ports. So you can measure input reflection, output reflection, forward transmission, and reverse transmission. Now, something as basic as the NanoVNA doesn't have the couplers or source on port 2. So you can only get a source out of one of the ports. That's okay. It's a fine compromise for saving $230,000. So what's a VNA good for? We kind of touched on this a little bit. The reflection measurements are good for measuring the SWR of an antenna or antenna system. Good for measuring the complex impedance of a device. Like you might want to measure the complex impedance looking into an antenna to design a matching network for it. Okay. It's even good for measuring components, resistors, inductors, capacitors, things like that. And you could also actually extract measurements like feed line length or distance to fault. These two require some additional computation within the device. We'll talk briefly about something called a time domain transform. But you can estimate, a feed line length or distance to a fault in a feed line from the same reflected measurements. Now, the two-port measurements, that's where we're supplying an input through one port and measuring through the other port, looking at the transmission properties. Again, we can look at the filter shape, look at the loss of a filter, insertion loss of a filter, the stop band loss of a filter, for example. Look at loss in a feed line, delay in a DUT, gain of an amplifier, these types of two-port device type measurements. It's all the transmission type measurements. So what does this mean? Well, we can look at things like antennas and duplexers, filters, inductors, capacitors, amplifiers, splitters, coax switches, phasing networks. All of these are things that, well, gee, sometimes as hams, we play with some of these things. So the VNA allows you to characterize the properties of these devices. So before I jump into S parameters real quick, I just want to stop and pause, see if there's any questions anybody has. All right, so everybody's got it, or everybody's sleeping. If you're sleeping, I appreciate the mute so that we don't listen to the snoring. So let's talk about S parameters. Okay, there's another one of those things that scares a lot of people. S stands for scattering parameters. And again, I know that doesn't help you. So let's look at really what it is. So an S parameter is simply a ratio. We were talking about ratios already, right? It's simply a ratio of a measured response to a stimulus. Notice the colors here. So in this case, an S parameter is the ratio of the response from the device measured on this port to the stimulus that was applied by this port. Okay. So S21, for example, would be the response measured at port 2 in response to a stimulus coming from port 1. Okay. So again, the response at port X from the stimulus to port Y, applied for port Y. Okay. I should say from port Y. So the S11 is essentially the measurement in the A receiver, right? The reflected energy divided by the R. Okay, so that's our reflected measurement. So that's really S11. So it's the reflection from the DUT port, the input port. Similarly, S21 is now going to be the response measured in the B receiver with respect to the signal that was applied, R being the reference receiver. That's it. That's what S parameters are. Now, you may also see that sometimes you see S22 and S12. Those two are using port 2 as the source. Okay, in the NanoVNA, you can't do that. So if you wanted to measure that, you would have to physically just turn the DUT around, right? Put the output port over here, and then you can measure the S12 and S22. But in most cases, all we really care about for most of the things we're going to do are the reflection properties based on S11, the through properties based on S21. That's really all you need to know about S parameters. They are a complex number, which means they have both a magnitude and a phase associated with them. So another thing that scares people away with VNAs is the fact that we got to do a calibration on it, right? I've got this antenna analyzer from MFJ. I don't have to do a calibration on that. Why do I have to do a calibration on a VNA, right? Doesn't it come calibrated? What's the story? Okay. Well, here's why we need what we call a user calibration. One thing is that a VNA, even these inexpensive nano VNAs, have a very large dynamic range, meaning that they can look at like loss to some really, really low levels, like 60 or 70 or 80 dB down, right? That's a huge change in power. And having that very large dynamic range means we want to remove any small errors that might be in the measurement system to take them out of our actual measured results. So that's part of what the user calibration does. Now, it also, what we're measuring phase. You remember what I said about phase? It's really just delay. So any interconnect that you have between the VNA and the device you're testing, that's going to introduce some delay. The VNA has no idea what that delay is going to be, right? And if you really want to calculate and measure the phase at your DUT ports, you need to be able to remove that delay or that phase of your interconnect. So that's also part of what happens with the user calibration. And that's called establishing a new measurement plane, so that we are essentially going to tell it, I want to make these measurements of magnitude and phase right at the connection point for my DUT. So that establishes that new measurement plane. So all the interconnect between your DUT and the cables and adapters and whatever it took to get back to your VNA can all be removed from the measurement, basically compensated out. And that's part of what the user calibration does. Now, of course, a factory calibration can't account for all of these things because it doesn't know what you're connecting to, how far away it is, what adapters you're using, or anything like that. So this is why we do a user calibration. Okay. And we want to do it whenever we have some kind of a configuration change. If you're changing your interconnect cable, it's got a different length, you're using a different adapter, you're measuring a different device, or especially if you're measuring over a different frequency range from the last time you calibrated, you want to calibrate again. It doesn't take very long. We'll walk right through it and show you how you do it. Okay. But this is why you need to do it, and this is when you want to do it. And the good thing is that if there are common measurements that you make, like I'm always going to measure this antenna over these frequency ranges, you can run calibrations, for those frequency ranges and store them, and then recall them later on, so you don't have to repeat that calibration again. So again, that user calibration corrects for what we call systematic error sources. And what are systematic error sources? They're basically things that are repeatable and are measurable. We're not talking about random sources like due to noise that will change every time you make a measurement. Systematic sources are things that are repeatable and measurable. Things like what we call tracking errors. Tracking errors are basically the frequency response of the source and the measuring receivers. They're not going to be perfectly flat, in terms of amplitude and phase over the wide frequency range. So what we do is we measure what they are and then remove it from our ultimate measurements. That's doing what we call a tracking error compensation. So also matching errors. Ideally the port impedance of the VNAs would be perfectly 50 ohms, but they're not. So there's going to be some mismatch, some reflections due to that. So any of those mismatches just due to the instrument itself, we want to remove those. So those are our matching errors, matching compensation. And then there's also leakage and crosstalk. These directional couplers, or the method that's being used to couple these things aren't perfect, right? Ideally, like this coupler would only respond to signals going in this direction. This coupler would only respond to signals going in that direction, but the reality is they have some residual response to the signals in the opposite direction. That's called directivity. Also, you might have some crosstalk between these ports, or if you're trying to measure a filter that has a lot of loss, at a given frequency, if you've got energy that's going around your DUT from port 1 to port 2, that's going to make your DUT look worse than it is, right? So by measuring that, we can remove that again from our measurements. So that's another systematic error that can get removed. And of course, establishing that new measurement plane to our DUT by calibrating out the interconnect cables and adapters and things like that. So that's why, hopefully I've justified why you want to do a user calibration, why you need to do it. So now on a VNA, how do we set up the displays? And the NanoVNA looks more complicated than it really is because it overlays all these displays on top of each other, the Smith chart and all these other plots, so it can get confusing. But keep in mind that you can choose to turn on and off various traces and have it only show one trace on one type of axis and make it very simple, like an antenna analyzer. But most measurements on a VNA are made versus frequency. I'm going to measure my 40-meter antenna from 7 to 7.3 megahertz, for example. Like I'm going to sweep an SWR, right? So we're making measurements with respect to a swept frequency. So things like the reflection coefficient, right? Signal being reflected back off the port. Typically, that's going to be shown as S11. And the display is going to be oftentimes we're just looking at the log magnitude of that. So it's basically the magnitude of that reflected signal coming back with respect to the incident signal. And then we do represent that in a log fashion. So again, we get that really large dynamic range. So like we said, if you've got a very well-matched device, you might be pulling the signal reflecting back off might be 1,000 times lower than the signal that's being applied to it. Okay. That's hard to see 1,000 to 1 on a linear display. It's very easy to see that when you convert it to a log display. Okay. We could also measure SWR. All right, and that's typically just shown in our traditional fashion in a linear way, showing 1.8 to 1, for example, right? We also can measure complex impedance. That's typically done on a Smith chart. We won't really get much into Smith charts in this talk here. I've got some videos on that topic if you want to get more into that. Really, really useful and very interesting thing, especially when you want to do things like matching networks, or it's really pretty handy to watch what's going on in the Smith chart as you manually tune your tuner. So I got a video on that too. The transmission coefficient, right, the through response of your DUT is, again, typically S21, again, typically shown as log magnitude. Things like insertion phase, group delay, etc. These are typically shown in a linear fashion. And then, as I mentioned, there's a time domain transform measurement that instead of making a measurement versus frequency, it's making a measurement versus time. So in effect, it's kind of like what's called a time domain reflectometer, where the result looks like we're sending a very short little pulse into a transmission line and then looking for when that reflected energy comes back and measuring the amount of time that takes. And then from that, we can compute distance. It doesn't really work that way, but the results are interpreted that way. We're actually doing it by doing what's called a inverse Fourier transform. But it's helpful when you're doing the transform measurements like a distance default or coax length measurement to change the response to linear instead of log magnitude, because that's going to give you a sharper point on the result. Log tends to compress things that have got a very large variation, so you kind of get this rounded type of thing when you have a small change. The linear response will be helpful to identify a particular point if you're trying to get a precise distance measurement. So with all that, that's kind of your basic VNA 101, okay? Applies to really just about any VNA. So now let's kind of talk more about the NanoVNA specifically. But again, before I go on, is anybody fuzzy on some of those topics, or just stop me and let me know? All righty, so let's talk about the NanoVNA specifically. Now, the unfortunate thing about NanoVNAs is that there are several developers and several variants. There's no one manufacturer of a NanoVNA. It really started off as a kind of an open source design project that was kind of published, and people started experimenting with it and doing some things with it, and then China Incorporated picked up on it, and everybody and the brother over there seems like was making versions of the NanoVNA. Some performing well, some not so well. So this is the price you pay for the price you pay. Okay. So the original NanoVNA, developed by a guy I think his name was Hugen, kind of responsible for initially commercializing it. So it was typically called the VNA H. Okay, it had a very tiny 2.8-inch diagonal measure display on it. In fact, and didn't even have a case. It just had a metal plate on the top and bottom, and then had like two boards bolted together, and the connector sticking out the side. And then later on, you started seeing some of the folks manufacturing them, putting them in an injection molded case like this. Okay, typically covered up to 1.5 gigahertz. The NanoVNA H4, okay, is basically the same design, but now with a larger 4-inch touchscreen display, and that's one of the ones I have here. I'm not sure if my video is showing along with the presentation or not, but I've got one of those sitting here. Really nice device. I still use mine quite a bit. So, but that's the H4, and we're going to focus a lot of the talk on the H and H4, even though there are later variants that came on we'll talk about here. So Paul was showing me his is a NanoVNA-F, and this was a different manufacturer, a different person basically took a look at what the NanoVNA did and said, yeah, I like what they did here, but I don't like what they did there, so I'm making my own. Okay, it's going to be very similar to the NanoVNA, but it offers some improvements. Those improvements were better dynamic range, a metal case instead of a plastic case, and also corrected one of the bigger faux pas that the NanoVNA's did. If you look carefully at these NanoVNA's, you see the ports are labeled CH0 and CH1. Now, the rest of the VNA world calls these port 1 and port 2. But the NanoVNA's, they're called channel 0 and channel 1. Can be very confusing. Well, channel 1 is not port 1, channel 1 is port 2. Okay, so they do correctly label the S parameters here, like the S11 is the reflection. We've got the source coming out of this port and then reflecting back, so that's where S11 is measured. But why didn't they label these port 1 and port 2 like the rest of the world? I don't know. The NanoVNA corrected that. So Paul, I'm sure if you look at yours, they say port 1 and port 2 like any good VNA should. Okay, again, the price you pay for the price you pay. Okay. Later on, we started seeing an improved performance device called the V2, also known as the SAA2, and these typically go to 3 or 4 gigahertz depending on the version. The biggest difference physically in terms of looking at it is that the ports come out the bottom of the display instead of off the side. Okay. Now this was as of late 2021, early 2022 is probably the last time I updated this presentation, as about 5-6 months ago. I still like the H4. It's stable, it's got decent support, pretty easy to get, and it was about $60. It might be a little bit more now with supply shortages and things like that, but that's kind of what I had. Now there's folks that have taken the V2 and put it into a metal case with N connectors instead of the SMA connectors, and that's called the SAA2N. And that's a 4-inch display, and that's a pretty decent unit there too. I've got one of those as well. Don't ask me why, but I do. So that's the 2N. Again, covers a little bit wider frequency range, a little bit better dynamic range. Okay, but it's substantially heavier because of the N connectors and the metal case. Okay. The guys that developed the SAA2 have developed a improved version called the V2+4. That's this guy right here. Okay, V2+4, that's this guy shown right over here. Okay, covers up to 4 gigahertz, much better dynamic range, and some but it's still the same basic functionality, but just better performance, a little bit faster sweeps, and better dynamic range. And now we're starting to see these guys develop more variations. There's a V2+4 Pro, and then there's a couple of other variants that have come along as well. I've started to lose track because I haven't been paying much attention. But they're all kind of based on the same basic functionality that we'll talk about here. So a little more detail, again, focusing that my detail is going to be more on the H and the H4. But all of the VNAs we've talked about are what we call 2-port, 1-path. And that's the block diagram I showed earlier. They have 2 measurement ports, right? Port 1 and port 2, but they only can measure 1 through path, right? Because they only have a source on one of the ports. So that's why it's called a 2-port, 1-path device. The H and the H4 go to 1.5 gig. The V2 versions go to 3 or 4 gigahertz. There are other models that go even higher than that. Okay, they generally all offer standalone operation, meaning they've got a built-in battery and you can use them, with the built-in touchscreen display. And for just about all of them, there's also a PC, one or more PC applications available. One of the more popular ones is called NanoVNA Saver. There's another one called NanoVNA QT. And these allow you to connect up to the device and use your computer in its larger display to make the measurements. That has some advantages, such as separating all the displays so they're not overlaid on top of each other, as well as extending the number of trace points being used and other things like that. So the basic details for most of the original versions can be found on this website here, nanovna.com. And that will bring up a little menu that you can learn about the VNA, how to use it, how to read the screen, how to calibrate it. All this information is available on that site. There's also a very active group on groups.io for NanoVNA users. There are other separate groups for the SAA2 and the V2+4. The V2+4, the group that's developing that, and they've made this not open source, so which is a good thing because now they control it a little bit better, and you're not out there finding as many clones and poorly made, copies. And that's nanorfe.com, and then there's the NanoVNA-V2, and there's a couple of other pages there as well. Okay. So that's where you can find, some information just online about the NanoVNA's. Again, the user groups and the email lists are pretty active. And there's also a lot of folks that are developing firmware for the units that really extend the capability and offer some improvements. We'll talk a little bit more about that in a moment. So this is under the hood of the H and the H4. Looks complex, but it really is pretty simple. Okay, so here are channel 1 and channel 2. Boy, I wish they were called port 1 and port 2. Excuse me, channel 0 and channel 1, which is port 1 and port 2. Okay, that's where that connects. Instead of couplers that I showed you earlier, it actually uses a bridge. Okay, so that's how we actually separate, if you will, the incident signal from the reflected signal, is with the bridge in a way. So there's the RF source is this little serial bus controlled SI 5351. It's very popular for anybody who's doing any hobby work, might have used this thing. It's a programmable RF source with multiple outputs. So its outputs are, creating the stimulus going out to the DUT, also creating the stimulus that's applied to a set of mixers. The bridge is used instead of directional couplers. It's a simple resistive bridge. So you think of it as a return loss bridge, or SWR bridge is really what it is. The SI 5351 also provides the stimulus, like I said, to our old friend, the SA612, which is the variant of the NA602, very, very popular Gilbert cell mixer. And the mixers are basically there to convert the RF signal down to the audio range. So we get audio signals out for our reflected signal, our reference signal, and our through signal. Those audio signals go now into a stereo audio codec. This is something that there's made in the millions, because a lot of commercial audio electronics, CD players, car radios, DVD players, that type of thing, have something similar to this. And this particular chip was available, and probably still is available, for pennies, because it's made in such large volume. So the developers of the NanoVNA, globbed onto that because they can get it cheap, and that's why the NanoVNA is cheap. It does all of the processing in the audio domain. All of that is controlled by a microcontroller, okay, that talks to this, through these little I2C, I2S buses, okay, and the firmware runs on that. That goes off and talks to the display. And then you've got your interface controls, the touch screen on the display, as well as push buttons or levers. And then also you got the power supply, USB interface, and the battery. That's really what's inside the NanoVNA. So let's take a look at the user interface for the NanoVNA. And again, it looks complicated. You got all these things laying on top of each other, but it really is not that bad. So on the top, there's a jog wheel that you can push to select things, and you can rotate left or right to move things, like up or down a menu or moving a marker back and forth. Okay. It is a touch screen accepts tapping to select things, as well as tapping and sliding to move things like a marker. And fairly simple menu structure once you get to use it, or once you get used to it. There's a home menu that has a display section. You open up that, and that lets you control things on the display, what traces you have turned on or off, what channels they're connected to, what format they're displaying in, and the scale that they're using. Okay, all things have to do with the display. And you have a marker menu to turn markers on. If you want to put any functions in the marker, like to do peak searches or something like that. There's a stimulus menu that allows you to set the start, stop, center, and span. Basically, what frequency range do you want to measure? All right, and then there's the calibration process. So pretty simple. When you do calibrations, we're going to talk about here in a moment how to do it. There are little memory slots you can save your calibrations into to recall later on, so you don't have to repeat the calibration for common measurements. And then again, there's a USB charging port, and the same port is used for the PC interface to use some of these PC software pieces. So let's talk about the calibration. One thing you got to think about is that the original firmware just supports 101 points across the frequency span. So depending on what frequency range you're using, you might have a pretty coarse or a coarse spacing, if you will, from one point to the next, because it's just going to take whatever that frequency range is divided by 101, and that's where the measurements are made, and that's where the calibration is made. So you have to be careful about that. You can say, well, why don't I just calibrate it from, from 1.5 megahertz to 30 megahertz, and then anything I measure in the HF bands is going to be calibrated. The problem with doing that is that the points where the calibration is being made are spaced so far apart that maybe only one or two of them land in each of the HF bands. And you're just relying on interpolation between those, and that's generally not good. So a wide range calibration is going to have a coarse spacing. So that's something to think about. Now, I've got a little asterisk here because later versions of firmware improves the number of points that you're using, as well as using the offline PC software. But regardless of the number of points, you're going to have the measurements are still going to be made at discrete points. So you're going to interpolate between them. So it's always a good idea to calibrate over the specific frequency range that you're measuring over. And again, other firmware developers, there's one guy out there that I like that's called Dislord is his name, the handle he goes by. He's got firmware out there that goes to 200 or even 400 points across the span. And it doesn't, obviously it takes a little bit longer to do the sweep, but it is nice to have that higher resolution. So on the calibration, it shows you on the NanoVNA what calibrations are being done. So that's this left-hand edge of the display right here. The first line will either be a capital C or a small c. The capital C means that we're calibrated for the current frequency range that you're measuring over. Good. A small c says that you've got a calibration that's loaded, but it doesn't match the frequency range, which means it's going to try to interpolate between the actual calibration points for your measurement points. Depending on how, it doesn't really tell you how much it's interpolating, but at least it tells you it is, so you can think about whether you want to recal over your specific frequency range. The number following that is the memory slot number that calibration is stored in. Okay, so that's what that means. If you have a star, it means you haven't stored that calibration, but otherwise you have a number there indicating what memory slot that's in, so you can recall it later. The next letters are, remember we talked about the various systematic errors that you can correct for with the calibration. So the D, R, and S stand for the directivity, reflection, and source match. So basically the tracking, the matching error, and the leakage and directivity errors. That means that you've done the calibration so that those things are included now in the corrections that are being made. All of these, the directivity, reflection tracking, and source match all apply to channel 0, reflection measurements, basically. The last two, transmission and crosstalk, these are your through measurements. So these apply to measurements that are going to be made for through measurements like amplifiers, filters, where you're using port 2 or channel 1. So these are required essentially for all the measurements you're going to be making regardless. And if you're only making reflection measurements like SWR measurements, you don't have to do the other calibrations. You only really need to do those if you're doing transmission measurements. Okay, looking at cable loss or filter characteristics or something like that. So here's the process. Here's how you use it. So this is on the display. There's the main menu. We hit calibration. That brings up the calibration menu. Okay, and then you start by hitting reset to clear the current calibration out. Once you've done reset, you go back to the same, you'll be left in the same menu. You hit calibrate. It will then prompt you to attach an open to the end of your cable or to the port, depending on where you want that measurement plane to be. You attach an open, okay? Well, you could just leave it open, but as you get higher and higher in frequency, it's actually a calibrated open, meaning that it's establishing the reference point, the reference plane at the same physical location, same electrical location. So you attach the open, hit open, it does a sweep, then it will prompt you to put on the short. You put that on, it runs the sweep on that, prompts you to add the load, which is a 50 ohm load. You run that sweep. That will get you through, and that's all you need to do if you're just making reflection measurements. If you're making through measurements, you want to do the last two, which are the isolation and through measurements. And then that would be, for the isolation measurements, you would terminate the channel 1 port to prevent any kind of stray pickup. For the through measurement, you connect channel 0 to channel 1. Okay, again, only required if you're making through measurements. Once you're done, you hit done, and then it'll prompt you to enter a slot 0, 1 through 3 or 4. And one important thing to remember is if you store something in slot 0 is recalled on power up. So if you always want to turn the thing on and be ready to measure your 20-meter antenna, do the calibration for 20 meters, store it in slot 0, and it's ready to be a 20-meter antenna analyzer when you instantly power it on. Okay. And again, you want to connect all of these standards, they're called calibration standards, ideally to where your device under test will connect, or more importantly, where that measurement matters. Like if you're measuring the SWR of an antenna system, you might want to measure where your transmitter connects, right? Because you want to see what your transmitter sees. If you really want to measure an antenna itself to design a matching network to be located at the antenna, then you want to establish a measurement plane at the far end of the coax if you can. Okay. So if you can't get to the far end of your coax for the measurement, you can do something called port extension. And what this allows you to do is, make your calibration measurements where you can, and then you're going to basically extend and say, okay, I'm going to make my calibration measurements at this point, but I'm going to go through a nice 50 ohm environment this much further to where my device is. And that will tend to remove the delay associated with that further interconnect. And that's what we call port extension. On the NanoVNA, this is actually not called port extension. It's actually called electrical delay. Okay, so that's the name of it on the NanoVNA. The rest of the VNA world calls it port extension. But that's how you move the reference plane from the point where you actually applied the standards to where your actual DUT is. Okay, so and you can, there's a way using the Smith chart that we're not going to get into. That's easy to kind of experimentally determine what that electrical delay is, where you basically connect up to where your device is going to be, replace your device with either an open or a short, and then adjust the electrical delay until the Smith chart shows a perfect open or short. Basically, it removes the phase rotation you see on the Smith chart. But again, topic for another video. So, but again, all of this is only important when you have to have an accurate phase measurement of your device. If you're just looking at SWR, you don't care. All right. All right, so let's talk about, setting the unit up. We've got to talk about things like channels and traces, right? So the channels are, channel 0 is our reflection port. That's where the source, the energy, or the stimulus comes from that channel. Okay, it's also called port 1. And then we're making our reflection measurements like SWR and return loss and things like that, input impedance, right? So that's display, channel, and then channel 0, reflect, okay? Channel 1 is your transmission port. So that's when you're measuring through a device like a filter or a piece of coax or something like that. All right, so that's called channel 1 or through. And then you then would say, I'm gonna assign some traces, and you can have up to 4 traces on the NanoVNA. And each trace can be assigned to channel 1 or channel 2. All right, and or you can turn each one on or off. So you may choose to only have one trace turned on, have it set up on channel 0, and make an SWR measurement, right? And then you can remove everything else, okay? But you basically assign any of the 4 traces to either of the 2 channels, and then tell it what it is you want to go measure. So again, common trace formats, we talked a little bit about this already. Typically, you have a display, select the trace you want to measure, and then tell it the format. Again, if you're making a log mag response or looking at reflection coefficient, you use log mag. If you're looking at SWR, you can just pick SWR and that'll be default to linear. Okay, so this just allows you to kind of go through and set that up. If you're measuring complex impedance, you would select the Smith chart. Okay, right here. Okay, so the channel 1 measurements are typically going to be log mag for S21 or maybe phase or delay. Okay, and of course there's other displays. Again, if you're not doing true RF design, you probably don't really care. To set the stimulus. Stimulus is just a fancy name for the frequency range that you're going to make your measurements over. Okay, so instead of like the old MFJ 259B where you got to manually adjust the dial across the band to watch SWR, you can plot SWR, much like something like a Rig Expert or something like that. Okay, and you can pick whichever is easier. You can set your frequency range by setting where I want to start, where I want to stop, where I want to, basically the starting and ending points of my sweep. That's typically handy if you're looking at, sweeping an antenna over a given amateur radio band. You could also pick it by picking the center frequency and the span around that center frequency. That's often handy if you're measuring a filter. You might say it's a bandpass filter that's centered at, at 29 megahertz, and you want to sweep, 3 megahertz around that 29 megahertz filter. Okay, but again, you could pick any combination of these to whichever is easier to set up the frequency range that you want. There's also a CW frequency setting where you can make measurements just at one single frequency, okay, much like an MFJ 259. So there's also markers you can turn on. The markers, when you turn them on, will show up on every display. Okay, so if we take a look at this display here, we can see channel 0. Okay, that's the yellow trace. It's the same color as the trace itself. So that's a reflection measurement. If it's log mag, that means it's the log magnitude of that S11 or the reflection coefficient. And it's on a 10 dB per division scale. So each of these divisions is 10 dB. And then the number after that is the location of the marker, okay, or the active marker. Okay, so channel 0, this green trace is also on channel 0, but it's measuring the complex impedance on the Smith chart. So it's using this circular chart with this little curly Q line in here. And then channel 0 here, this blue one, is measuring SWR. That's this guy down here. And you can see a couple of markers on there as well. So again, up to 4 markers are available. You can use the jog wheel or the touch and drag on the screen to move them. When you do a delta marker, it's going to show the delta. Like right now, the active marker is marker number 2. The delta tells you that this is the difference from the position of marker number 1. So you get the delta markers as well. And then the marker values are as we described here. Okay. The selected marker is shown there. The delta from the previous marker shown here. All the markers track each other on all the displays. So if I move the frequency of this marker back and forth, it's going to move on all the other traces the same way. You do have search features to move to the min and max left or right to find a peak and something like that. And you also have marker operations. You can actually set the center frequency or start or stop frequency or span based on the marker locations. That can be very handy if you're trying to measure some unknown crystals, for example, which are very, very narrow band devices. You might start off sweeping wide and you see where the little peak is. You can put a marker on either side of it and tell it to set the frequency span based on those markers and then resweep based on that. And of course, it lets you also choose the units used in the Smith chart, whether you want to actually show resistance and capacitive or capacitance and inductance, or if you want to show the reactance, you can have that show as well. But again, if you're not into Smith charts, just turn it off and you don't have to worry about looking at it. So here's the basic process for setting up the NanoVNA. Typically configure which traces you want turned on, how many of them you want on, what channels they're connected to, and the formats you want. It might be as simple as saying, I want one trace on channel 0 doing SWR. Done. Okay. Or then you want to set up a stimulus, what frequency range you want to make your measurements over. And the reality is you can do these two in any order. Okay. Whatever is easier for you. And then you want to run a calibration over that stimulus range and save it. and then connect up your device and run your tests. And then you might use markers and things like that to extract values off of that, or just watch what's going on. Okay. And then you can adjust traces, change your formats, add other traces, because even if I add other traces, I don't have to redo the calibration, because all of the traces are computed from the same set of the measurements coming from the receiver. So it doesn't matter if you set up the calibration with only one trace turned on. If you turn on another trace, you're still measuring over the same frequency range. You don't have to recalibrate. Okay. So here's a couple of examples of what results might look like. So here's measuring an antenna. I've got the antenna connected up to channel 0 or port 1. Down here along the bottom, it's showing me the frequency range. The start frequency is 7 megahertz, the stop frequency is 7.3. So I'm obviously measuring my 40-meter antenna. So the SWR plot, again, you can kind of look at the color of the trace, look at the color up here. Okay, same color, channel 0. So it's on channel 0. It's formatted for SWR. The scale is 1 per division. So down here is 1 to 1, 2 to 1, 3 to 1, 4 to 1. Okay. And then we could actually see my marker, which I didn't move, is still sitting at 7 megahertz right at the beginning. And we can see right there, my SWR is 4.73 to 1. Okay. And it's going down to about 1 to 1 right down here. Okay. The complex impedance shown on the Smith chart. Okay. That's this curly Q trace right here. And that's using the circular and arcs of the Smith chart. The only thing you might want to remember about the Smith chart is that the bullseye of it right here in the center of the outer circle is the 50 ohm point, or the match point. And everything else above this is, it's got inductive reactance to it. Down here has capacitive reactance. And we can see there is a frequency where you get really close to 50 ohms. And that's going to correspond to this frequency right here. All right. The yellow trace right here, take a look up here. That's also on channel 0. And log mag means it's the log magnitude of S11. So it's the reflection coefficient. And we can actually see, obviously, that's got a minimum boom right down there at the same frequency at the minimum of the SWR. Okay, because they're just mathematically, related to each other. You also will notice that it's easier to define that minimum on the reflection coefficient than it is on the SWR plot. The SWR plot might be kind of shallow, right? So if you want to find the exact point where you're tuned to, right, then the reflection coefficient gives you kind of a sharper indication. But they're both showing you the same thing, but with different formats, if you will. So let's say I want to measure a filter, okay? In this case, the filter that I measured here, connected between channel 0 and channel 1, is a low-pass filter that I designed to stick on the back end of a Michigan Mighty Mite 3.5 megahertz CW transmitter. So I wanted to knock down the second and third harmonics, from that transmitter. So let's take a look at what we have. So I've got, in this case, my start frequency at 1 megahertz, my stop frequency at 15 megahertz. Okay. And so that's my frequency range. My insertion loss, which is also the measurement of the transmission properties. Okay, you can see the blue trace. Blue trace is on channel 1, so that's measuring my through response. I'm measuring the log magnitude of that. And what I can see, again, a perfect through with no loss would be 0 dB, and that's where we're sitting at right up here. And we can see we get out to 7 or 8 megahertz, and this thing starts coming down, indicating more and more loss through the filter. I got the marker sitting out here at about 10.5 megahertz. So that's at about the third harmonic of my 3.58 megahertz transmitter. And that's showing me that my third harmonic will be attenuated by about 47 dB. Okay, so that's the insertion loss. I've also got the SWR plotted here, right? See the purple trace, channel 0, SWR. We can see it's got a pretty low SWR, below about 1.5 to 1, until we go past the corner of the filter, and then the SWR rockets up. Okay, and that's kind of how this filter works, is that frequencies outside of its low pass bandwidth are reflected back and not allowed through. So we can see that's why the SWR gets rocketed up. Okay, And similarly, I've got the reflection coefficient. Okay, again, just different math on that same reflected measurement. And we can see its reflection coefficient is down, 10 dB or more, 8 to 10 dB down here. And then it kind of gets up to, at higher frequencies, it's close to zero, meaning that all of the energy at these frequencies, or nearly all of it, is being reflected back, right? The only thing getting through is something that's about 47 dB down, which is minuscule. Okay. I also had the input impedance on here, which I could have just turned it off because I'm not really using it in this case. It's just showing me that at these lower frequencies, the input impedance is close to bullseye, close to 50 ohms, and it gets further and further away from that, the higher and higher you go in frequency. Now measuring coax length, that's what I mentioned that's actually a computation that's done based on the reflection measurement. So here's my open coax sitting here. We run that transform function in the NanoVNA, set the format to linear, and you get this nice sharp response. And what this is showing you, this is notice the axis down here is time. You can think of this as that if I had sent a narrow little electrical pulse down the transmission line, it ran down the line, hit the open circuit, got reflected back, and then got picked up again and measured here. So this time is the round trip delay between this port right here out to the reflection at the end of the cable, and then back to this port again. So that's my round trip delay. Now you can tell the NanoVNA what the velocity factor is of your coax, and then it can then compute the distance for you. In this case, it was 9.13 meters, or about a little over 20 feet. That uses the time domain transform. Now, if you turn the transform off, you can connect up the other end of the coax to port 1 and measure the insertion loss. So you can measure the loss of coax over frequency. You don't get both of these at the same time. I just happen to use the same display here to show you that. So different ways of measuring coax, both length and insertion loss. So the insertion loss is very similar to the process of measuring a filter. So those are some of the basic applications that most hams will use. But so now it's time to talk about the good, the bad, and the ugly, with apologies to Mr. Eastwood. There are obviously some limitations and downsides to the NanoVNA compared to these multi-$1,000 professional units. So let's talk about what some of those are. I mentioned one earlier, that generally only 101 trace points. Again, external software helps with that one. You can get software that will give you, a couple of 100 points. I should say firmware that uses a couple of 100 points, or using some of the PC-based software, you can actually get many more points than that, thousands of points if you want really high resolution results. But it's important to recognize that you may have some very limited measurement resolution just due to the coarse spacing of points over your frequency range. One of the other bigger limitations, or things to think about anyway, is that the RF output of the device is not a sine wave. It's a square wave. Okay, and that holds true for all of the NanoVNAs that I've looked at. They're all square waves. The original versions, like the H and the H4, take this even a step further, is that when they measure higher frequencies, they're using the odd harmonics of that square wave, okay? The V2 versions will run a square wave all the way up to the 3 or 4 gigahertz, okay? But the H and the H4, even though they can measure up to 1500 megahertz, the square wave doesn't go up that high. The square wave only goes up to 300 meg, okay? So when you're making measurements up to 300 megahertz, it's using the fundamental of the square wave, okay? But if you're making measurements between 300 and 900 megahertz, it's actually using the third harmonic of that same square wave, okay? And above that, it's using the fifth harmonic, right? Because a square wave consists of energy at the fundamental frequency, as well as the odd harmonics above that. So this output that we see right here, this happens to be a 200 megahertz square wave. So that means I could be making measurements at 200 megahertz, but this same exact waveform is what's used to make measurements at 600 megahertz and at 1 gigahertz, because that would be at the third and the fifth harmonic, okay? Also, so you have to think about the device that I'm testing. Will it care that it's being hit by a square wave instead of a sine wave? What's it going to do with the energy at those harmonics, right? And does it care, right? Some cases it won't care at all, right? In fact, most of the antenna analyzers are out there work the same way. You just didn't know it, okay? Also, the other thing is that with many of the NanoVNA's, the output power is not adjustable. Okay, so it's a fixed amplitude on this square wave. So this is like 600 millivolts peak to peak on the H and the H4. So that translates at the fundamental frequency to about a milliwatt of power, a little bit more than a milliwatt, 0 dBm to about plus 2 dBm, which is basically a milliwatt to a little bit to close to 2 milliwatts, all right? But when you're making measurements from 300 to 900 megahertz, you're about 10 dB lower than that. So instead of a milliwatt, you're about 100 microwatts of power. About another 10 or 12 dB below that for higher frequencies. So now you're down, at 10 to 15, 20 microwatts, or even less than 10 microwatts of power. And you can't adjust it. And they're all there. So let's say I was trying to test, an amplifier that I made for 900 meg. Okay, great, that's this. But that input of that amplifier is also going to be hit by energy at these other frequencies as well, because it's being hit by the square wave. So you have to think about whether that's going to be okay for your device, and whether the power level, whether it might be too high for your device. If you're trying to measure an LNA, this power level is a lot higher than it's going to see in the actual application. You might saturate the amplifier. So you might have to use something like an attenuator or something like that ahead of, between the NanoVNA and the amp, so you don't overload the amp. So again, you have to consider the device that you're testing and whether the output power that the NanoVNA is producing is going to be okay. You're not going to get any gain compression. You're not going to get any limiting, those types of things. So you have to think about those things. Again, some limitations. Also, the receive reference level, both in channel 0 and channel 1 is not adjustable. So if you're measuring something like an amplifier that's got 20 dB of gain, you may have to then attenuate that output by 20 dB before you feed it back to the NanoVNA, so you don't overload the VNA. Okay, so you have to think about that. So you do have a somewhat limited dynamic range. I mean, the NanoVNA still measures much higher dynamic range than many other instruments. It might be 40 or 50 dB dynamic range, but compared to professional units, which would be 90 or 100 or 120 dB dynamic range, the NanoVNA's are much more limited, but again, perfectly adequate for most of what we're doing as hams. The resolution bandwidth, if you're familiar with that term from spectrum analyzers, is not adjustable. With some versions of third-party firmware, there is some small adjustability of the RBW, which will help determine the noise floor and the ability to see very narrow band devices and things like that. Again, some third-party firmware addresses that. Now, of course, there may be other limitations as well, but this is kind of the major good, bad, and ugly points of the NanoVNA. So the summary of this is that, the NanoVNA, I kind of called this the RF tool or toy of the year, and that was probably when I first put this presentation together, probably 2 or 3 years ago. But it still kind of holds true. I mean, for the price of this thing, amazing capability for typically under $100. I'll say that now. You probably still get some for around the $60 mark, right? But pretty amazing capability for that. But you get to some of the more advanced ones like the V2+4, that's closer to $200, but still, 1.5 orders of magnitude cheaper than a professional unit. There's a ton of videos out there, lots of resources to kind of go learn how to use it. My YouTube channel has got a whole playlist on NanoVNA's that you're more than welcome to go watch and use. And again, pretty active user groups to kind of help you get through it. So a good US source for these things, where I've purchased 2 of mine, is R&L Electronics. They usually have good things in stock, and they generally try to ensure that the devices that they're getting are ones that are not from some of these makers that are doing a poor job in building them. So anyway, I want to thank you for that. A little self-serving plug here. I do have a YouTube channel. That's youtube.com/mycallsign. This QR code will take you right there. Never mind the Morse code key and the transistor. just kind of reflections of some of my things I'm interested in. But got well over 350 videos on the channel, over 170,000 subscribers and 20+ million views on these videos that I have. So, and they cover everything from basic electronics tutorials, test and measurement stuff, amateur radio things, and some repair videos and that type of thing. So I think that's all I've got, Paul. We want to open it up for questions. So I can keep the presentation up if you want to scroll back to something. If not, we can kind of revert back to video.
Yeah, if anybody has questions or comments, go ahead and unmute yourself and pipe up.
I just want to say I thought it was very well done. Appreciate the information.
Oh, thank you.
All right.
That's definitely interesting presentation. I need to learn my NanoVNA better. I have the F version.
Okay.
But I use a Keysight Field Fox at work.
Oh, there you go. So you're already
That thing I know
familiar
how
with
to
the
use
terms.
inside and out. The NanoVNA, I'm still discovering things because I haven't sat down with it for long enough. But
Yeah, well, certainly the NanoVNA menu structure and the Field Fox menu structure look nothing alike.
No.
So,
no, they're not. And we just got a new Field Fox because we had an older one.
Okay.
And even the newer one has added things that I'm finding in there and didn't know were there. So
okay, very good.
Yeah. More hams should have these things because they're so cheap. So
Yeah, like I said, I mean, I've got a couple of these, as you saw. I got there's the H4, there's the SAA V2 or the 2N, and then the newer one is the V2 plus 4. But I've also got like a rig expert. I've got an AA55 Zoom rig expert. And the problem you'll find is that these inexpensive things are great, but the display is going to wash out pretty quickly and easily on if you try to use this outdoors when you're tuning an antenna. Also, I wouldn't want to drop this on the ground because it may not survive that. The rig expert probably will. So
the guys that made the plus 4,
yeah,
it's like the HCS group, I believe they're called.
I think so. Yeah.
They're promising a new NanoVNA that's coming out that's going to be a few $100, but it's got like greater than 100 dBs of dynamic range. I'm really interested to see if they can bring that to fruition.
Yeah, because I heard I think it goes up to 6 gigahertz, about 100 dB or more dynamic range, and that's getting into the professional territory, right? You get into look at like a Copper Mountain, USB VNA, and they're typically 110 dB dynamic range, 120.
Yeah.
But you get into something like that for them for a couple of $100. I mean, you could do a nice job, tuning duplexer cans and things like that with an instrument that costs $200. Pretty amazing.
Sure.
I do have one for you.
Interesting.
Go ahead.
Sorry to interrupt.
Oh, go ahead.
Being a newbie to the instrument, I know you said it does the SWR, but does it show the wattage?
It does not. So it's not an RF power meter. All it will do is it'll show SWR from its own stimulus. It's not like an SWR meter that you stick in line where you're using your transmitter as the stimulus. This is more like an antenna analyzer where you're making a measurement connecting your antenna to the one port of the VNA and letting it do its sweep, okay, and show its response. So it's generating the stimulus and the response. So it's only putting out like an HF, like I said, about a milliwatt of power. It's not going to show you that, and it's not going to act as a watt meter or anything like that. So if you want some kind of an inline watt meter and SWR meter, then this doesn't take the place of that. This does allow you to do tuning and adjusting of antennas without employing your transmitter to do that, because oftentimes maybe you can't turn the transmitter down to such a low power level. SWR is not a function of power. Okay, so it's perfectly fine to make the measurement at a milliwatt of power. The only place where you could run into an issue with that, and it's not uncommon, is if you're measuring a big HF antenna. That big HF antenna might be picking up a lot of signals off the air. And those signals off the air might actually will get back to the VNA. The VNA has no way of determining whether the signal it's seeing coming back is coming from reflected energy from its own stimulus, or energy that's picked up and being measured. So that's one time where you can get erratic readings sometimes if you're measuring a real deployed antenna, especially large antennas, or if your band conditions are such where you're seeing a lot of 20 and 30 over signals. You might essentially inject those signals into the NanoVNA and cause what might look like erratic readings that don't look so erratic when you do an SWR measurement on your rig with a regular SWR meter.
Thank
All
you.
right. Anybody else? All righty. Then Alan, thank you very much.
Sure.
And I'm going to definitely check your channel and see some of the other topics you've got presentations on. And I have a feeling that we will be inviting you back to speak on something else.
Sure. Like I said, I got most of my, as I work for Tektronix. I've got a ton of videos on how to use an oscilloscope to do things. I've got a lot of spectrum analyzer videos. I've got a lot of the NanoVNA. I've also done some amateur radio reviews, like got a review on one of the Rig Expert things. More recently, I just did a review on a little FX4C SDR transceiver out of China, little QRP transceiver. I just did a review on that. So, but and then there is a actually what I'll do, if you indulge me here a little bit, let me share my screen here one more time. Let me see here. Let me go and find this guy. If I go and share the screen, this is actually what my channel looks like. You can get to it just by youtube.com/W2AEW, even though this URL here looks a little funky. But what I wanted to show you here is that, here's, a lot of the videos that I've got up here. My most popular video has been viewed almost 700,000 times on the basics of an op-amp circuit. But what I want to point out to you is this thing right here. There's a link to a video index file. And what that brings you to is a PDF file that is an index of all the videos that I've done. Every one of them is hyperlinked. The first part of this, the first couple of pages of this is just a numeric list from video number 1 all the way up to video number 356. Beyond that, it's kind of arranged by topic. And it's gotten to the point where I probably have to start doing this better, but like, here's videos that are all just having to do with oscilloscopes. And here's videos on spectrum analyzers and other test equipment, test procedures, circuit construction, circuit theory, and then various components, like just a bunch of videos I have on different types of diodes. Okay. So, and a lot of amateur radio operation, equipment and radio repair, and some specific radio stuff kind of pulled out here. So you can search this and then click on any one of these, will take you to that video.
Very cool. All right. Well, we really appreciate this. Was educational.
Right,
and I need to learn to play with this a little bit. I've tried a little bit, but yeah, I need to experiment more with it.
Yeah, the unfortunate thing is I think like the default setup that they have stored in slot 0 is like 1 megahertz to 900 meg with 4 traces turned on, including the Smith chart. You turn it on, it's just a mess of traces, and you're like, what's going on here? Yeah. It'd be almost easier if you just say, if most of what I want to do with this is do SWR sweeps, set up your own calibration over the frequency range you're most often going to use with just the SWR plot on it and nothing else. Save that in slot 0. So every time you turn it on, that's what it looks like. So.
Yep. Very good. All right. Well, thanks everybody. If the local guys want to hang on for a little bit, we'll briefly discuss field day, and I will let Alan go. And once again, thank you very much.
All right. Thank you, guys.
Good night.
All right. Take care now.
All right.
Thanks.
All right.
Okay. So we are planning to do field day. And we are going to be doing it out at Joe's. We're gonna get an email out to everybody with the details on it. So we're gonna set up, and we'll put out a request for people to bring, this food or whatever we need to do. But we are definitely going to be doing field day again, so prepare yourself. And thank you very much, Joe, for offering to let us invade your farm. So, all right, everybody, have a good night. And I've got a few more that I've been in touch with. One of them is, and I had totally lost track until I ran into him again at Dayton. One of them is, this card is Dan White, who is a professor at VU. Who is seriously into satellite operations. And he said, how about instead of me doing a talk there, he said, why don't you guys just come over to my lab and I'll show you some stuff. So we're going to arrange that. I'll find out from him when the best time to do that. Most likely it will be during the summer before classes start back up. So I'll get that arranged, and I will send out an invite. And then we will just show up at his lab over at Valparaiso University. And he's going to go over some in-depth stuff on satellite communications. So, all right, everybody, enjoy your weekend. And
Hey, Paul.
I'll talk to you later.
Hey, Paul.
Yes.
Yeah. Have you thought about K3LR?
Yes. We've had Tim speak once, but it was several years back. So I can reach out to him again. And I'm sure he'd be happy to come in and talk to us.
Yeah, another good one tonight. Thanks a lot.
You're welcome. Everybody have a good night.